Yes, sir.
Yeah, all right. Let's begin then. So we were looking at hashing in particular yesterday, and we looked at applications of hashing, wherein we saw basically at a very high level we saw two types of patterns. I will just summarize that once in the interest of everyone. So we were basically looking at hashing yesterday, and these are the two patterns that we primarily looked at. Basically, we saw that typically hashing is used in cases when you have to reference to an element which has occurred in the past. So when you have to search an element that occurred in the past, then typically you use hashing, or you typically store that element in the hash table, and you at that point in time when you want to reference it, you search for that element in the hash table, and that searching is efficient. So we looked at a lot of problems with this type, like group anagrams, brick wall, and what was another, fraction to recurring decimal. So these were all problems of the same type. We also looked at subarray sum, and the second pattern was we basically looked at questions wherein we need to explicitly store a mapping, and there are questions that warrant such kind of a data structure like a hash table, wherein we say that for instance, we looked at the problem of copying a linked list, right? Making a deep copy of a linked list. So with random pointer, we saw that, and we saw that we basically have to do nothing but store the store the references of the old list to the store a mapping from the old list to a new list, and that is basically what we use in order to make a deep copy of the list, right? And towards the very end, we were looking at problems of this type, in which we saw a view of the subarray, which is very important and comes up frequently in scenarios. So basically, we looked at we took this example of finding all, or finding the number of subarrays with a given sum k, and we saw that basically there is a view of subarrays that for our purposes is very useful. Basically, we said that uh, any subarray ij is basically sij is nothing but you can take s0 to j, and you can subtract s0 to I minus 1. So basically this entire prefix array minus this array gives us this subarray, and this is the view that we use to optimize search over subarrays. How do we do that? uh, First of all, this view was clear to everyone, right? No one had any questions in this? No, Shravan, you haven't missed anything. This view was fine to everyone? Fine with everyone?
Yes.
Yeah.
Yes.
So we use that view basically to say that when we have to search over subarrays, we will optimize our search. So in general, how do you search over subarrays? You basically fix there are like many ways you can do that. One way is that you fix an ending index and you enumerate all subarrays ending at this j. So how do you do that? You traverse backwards from j. You traverse j minus 1, j minus 2, j minus 3. So each of these is a subarray ending with j. So you keep doing this till 0. So this s0 to j is the final subarray ending with j, and then you move on to j plus 1, and then you again enumerate all subarrays ending with j plus 1. So this is how you enumerate all subarrays, and this method of enumeration typically takes n square time, right? And so this is, and we saw that what we can do with this one together with the view of the subarray that I told you helps us in performing search over subarrays efficiently. How is that? Basically, what we do is when we fix a particular j, when we are at a given j, what we do is when we have to basically check for a property for all subarrays ending at j, right? And that property we basically check by checking for all the prefix arrays before j. So we check for the existence of that property amongst all prefix arrays before j. So this, and if that property is satisfied, then we say that then this subarray is in our resultant answer, right? And this search over all prefix arrays, we typically optimize this search using a hash table. So this is the abstract idea. I mean, let me make this more concrete with the help of the example that we took. So basically, in the question that we looked at, we had to enumerate all subarrays with a given sum k, right? So let's see. So this is a subarray question. The first thing that I see is that this is a subarray question. So subarray questions, at least two things comes to my mind. Either I try 2 pointers, and also I try this view of subarray that I gave you. So let me try this. So now, so the first thing I saw in the question is that it's a subarray question. Then I told myself, okay, if this, let's try this view of the subarray pattern, and let's see if we can get anything, achieve anything out of that. And then we said that, okay, so what do I have to do? I have to find all subarrays ending, all subarrays with sum k. So basically that total answer is nothing but all subarrays ending at 0 with sum k plus subarrays ending at index 1 with sum k plus subarrays ending at 2 with sum k, right? And so on till subarrays ending at n minus 1 with sum k. So this is basically how I will enumerate all the subarrays, right? I just told you that. How do you enumerate a subarray? All subarrays, you fix a j, an ending index, and then you enumerate all subarrays ending at j. So our property that we need to satisfy is that I need to find all subarrays with sum k, right? So let's talk about a particular index now. So I know this is the first thing that I wrote down. Now let's see how do I solve each of these individual problems, right? So what do I have to solve now? Now I have to solve that how many subarrays exist which end at a particular index j and have a sum of k, right? This is what I have to solve. Now, when I'm solving this, I use the view of the subarray that I know. So what is the view? The view is that if I have to find subarrays ending at j with a given property, I basically will find prefix arrays before j which satisfies some other equivalent property, right? Such that I get this subarray with the property that I actually want. So what is that property of prefix array that I'm looking for here? So I know that this total sum is S and this sum that I need is K. So I need prefix arrays of sum S minus K, right? So basically what I need is if the total number of subarrays ending at J with sum K is basically equal to the total number of prefix arrays before J with sum S minus K. This is what I wrote down from the view of the subarray that I gave you, right? And now, so this is part B. I just use the view to arrive at a property that I am searching for amongst the prefix subarrays, right? And then finally, I will have part C, which is basically now I have to search. So this searching of prefix arrays, I will optimize through hash tables. So basically I say that when I came here, I could store all the prefix arrays with sums, right? When I am iterating or traversing from the left to right, I could store all the prefix arrays with sums, because I can take cumulative sums. And so I know prefix arrays with sums, and I can store the frequency of each of that in a hash table. So I can store prefix arrays with sum 5, the total number of prefix arrays with sum 5. I can store the total number of prefix arrays with sum 2. All that till I reach J. So this I can populate when I'm actually coming to J. So then basically what I have to do is I just have to look for, in this table, I have to look for T of S minus K. And that is basically the total number of subarrays with some S minus K. Total number of prefix arrays with some S minus K, which basically means that this is the total number of subarrays ending at J with some K. Right? So I can add that to the result. And of course, now that I am here, this total prefix sum, I can increment the appropriate counter in the hash table for this sum. So whatever this sum was S. So I can do a T of S plus plus, so that I increment the counter here, and then I can move on to J plus 1 and repeat the steps A, B, C, right? And I can keep doing that till I get the result, right? So is everyone clear with this entire approach of subarrays? 3 steps I told you. Any questions in this? Is this crystal clear to everyone? Is there any doubt? This will come again and again. So make sure it is crystal clear to you, the approach. Is this clear, guys? So 3 steps I told you. I told you a way of iterating. So basically all subarrays is nothing but subarrays ending at 1 plus subarrays ending at 2 and so on. Now for subarrays ending at a particular J, you need to find prefix arrays before J with a certain property. So that's part B. And then in part B, you find out that property. And then in part C, you basically search all the prefix arrays with that property. And that searching can be efficiently done using hash tables. So that's basically the approach we use for this kind of a question. So if this is clear to you, then did you try this question? Subarray sums divisible by K? This is question number. This is 974. Were you able to do it? Should I discuss it? Yeah, I can discuss. What about others? How many of you actually tried it? Yeah. Okay. Cool. Let's do it then, basically. So see, basically you have to, it is very similar to what we have discussed. It's just that the finding that property will be a little trickier. So first things first, what is the pattern that I notice in the question? I see that I have to find subarrays with a given property, right? This is how I look at the question. This is an abstract view of the question. So subarrays with a given property, as in I have to find, what is the property? You have to find subarrays which are divisible, whose sum is divisible by K. This is the property that I'm looking for. So immediately the first thing that comes to my mind, or one of the things that comes to my mind is, let's try the view of the subarray. So from the view of the subarray, I have 3 points or 3 steps that I will use. Basically, what I'm saying is all the subarrays, the total subarrays is basically subarrays ending at 0 whose sum is divisible by k, plus subarrays ending at 1 sum divisible by k, plus subarrays ending at 2 divisible by k, and so on, plus subarrays ending at n minus 1 divisible by k, right? So this is the answer. This is the first step. The next step is subarrays. How do I find out all subarrays ending at a particular j whose sum is divisible by k? So now I tell that subarrays ending at j with sum divisible by k is basically equivalent to prefix arrays ending at I less than j with some other property p2, right? And in B, I have to find this property. So what is this property? Can anyone tell me? People who tried?
So we can divide the complete array by k, and then the remainder, whatever the remainder comes, we search for it throughout the previous.
You can divide the complete array by k.
So then in that case, we will get like negative numbers. So when we find the prefix sum, like for the negative numbers, like if we are searching for sum minus k, then it is efficient to add another k and then divide it by modulus.
That's okay, but what is this property p2 that prefix arrays need to satisfy so that this particular subarray becomes divisible by k? I am looking for that.
Sum of the prefix array should be equal to the remainder of the complete array when divided by
Right.
k.
Right. So that's one. Let's see. So let's calculate the, let's see how we come up with this p2, and this is basically the crux of the question. So see, you have this array. So at any index ending at j, you have to, so let's take any subarray ending at j. You have to, let's say this subarray is divisible by k. I mean, this subarray satisfies the property. What does that mean? That means that this particular sum sj, so this particular sum sj modulo k is 0, right? So now let's see. Let's say this entire sum was s. Okay. So now let's see. So what I have to, and this sum is si. I have to basically relate si with s and sj. I mean, the property basically. So if, let's say s, when I divide it by k, I can write s as q1 into k plus r1. Correct? So I have done nothing but divided s by k. And I can write si, let's say when I divide si by k, I can write si as q2 into k plus r2, right? R1 and R2, where R1 and R2 are between 0 to k. K is open and 0 is closed. That's the, this is the remainder theorem, right? Everyone knows this. No one has issues with this, right? Yeah. So I know that Sj is nothing but S minus Si. Yeah. So Sj is S minus Si, which is basically Q1 minus Q2K plus R1 minus R2. Now I know that I need Sj to satisfy some property. What is the property? I need Sj to be divisible by K. So what does that mean? That means that I need this entire thing to become some C into K, right? That's how it will become divisible by K. So now let's see what are the cases when this becomes C into K. So let's first assume that the remainders are only positive. So if remainders are between 0 to K, as in 0 to K minus 1, K is not included, then R1 minus R2 is in what range? R1 minus R2 is also in 0 to K. Right? So now if R1 minus R2 is in this range 0 to K, then this, for this entire expression to become C into K, this has to become 0, right? Because it cannot, it is not taking any value greater than equals to K, right? Had it been taking greater than equals to K, then also it might have been possible that this entire sum would have become a multiple of K. So basically for this to be true, R1 minus R2 has to be 0. So R1 has to be equals to R2. So what is the property? The equivalent property is that the remainder that S gives on dividing with K has to be equal to the remainder that Si gives on dividing with K. R1 and R2 are those, right? Yes, yes, I'll come to that. I'll come to that. Don't worry. First of all, till here, this is clear to everyone how I arrived at a property in terms of the prefix array. The prefix array and the entire array. Right? So, okay, if this is clear to you, now let's shift gears. Now see, but the actual problem is a little more involved than that. We wrote S is basically Q1 into X plus, sorry, Q1 into K plus R1, and Si is Q2 into K plus R2. The problem here is that S and Si can be negative. Okay, so just to give you a heads up, when you write minus 12, let's say you are basically trying to divide minus 12 by 5, let's say. So minus 12 can be written as minus 3 into 5 plus 3. Or it can be written as minus 2 into 5 minus 2. So both are equivalent. So in C++, when you divide or when you take the remainder of a negative number with let's say a positive number, what it does is it gives you this and not this. First of all, this part is clear to everyone, the negative part, how C++ treats it. So this is how C++ treats it. I mean, you cannot do anything about it. It gives you, when you divide a negative number with a positive number, it gives you a negative remainder. So basically this is how it converts it. So if this is the case, then let's talk about the range of R1 and R2. So if S can be negative as well, then what can R1 take? R1 can be anything from minus K minus 1 to plus K minus 1. right? Just see this. This can be from minus k minus 1 to k minus 1. Similarly, R2 can be in this range if negative numbers are also included. If you are accounting for negative remainders, then R2 can also be in this range, right? So now when you do Sj as S minus Si, can you mute? Who's that? Radhika, can you mute? Yeah. So Sj is S minus Si. So this is basically Q1 minus Q2 into K plus R1 minus R2. So what is the range of R1 minus R2 now? Tell me. Can anyone tell me what is the range of R1 minus R2? If R1, do you understand that R1 can take this range and R2 can take this range if remainders are negative as well? So R1 minus R2, rightly as Karan said, can take anything from minus 2 into k minus 1 to 2 into k minus 1. So now let's come back to the same problem. Now you are saying that you want this entire expression to be c into k. Correct? So in this range, what are the cases when this entire sum can become a multiple of k? When this, so it is basically just minus 2k plus 2 to 2k minus 2, right? So you have a minus k here, 0 and a k in between, right? You have these three quantities in between. In this range, you have these three quantities, and for these three quantities, this entire thing will become c into k, right? So if you want to extend this for negative numbers, then basically what you have to find is you have to find all prefix arrays such that the difference R1 minus R2 is either minus k or 0 or k. All the three, and you have to sum them, sum the total number of such prefix arrays. So R1 is basically nothing but S modulo k, the total sum modulo k, and R2 is Si, the prefix array modulo k. Now ask me questions if you don't understand anything. This is the final condition if you are including negative numbers as well. Can it be minus 2k, Shravan? This is till 2k minus 2. Draw the number line. This is 2k minus 2. 2k is greater than 2k minus 2. This is minus k. This is minus k minus 1. You do that till this is minus 2k. So this is minus k minus 1 minus 2k. Here you will have a minus 2k plus 2. So you are looking for this range. In this range, you just have a minus k, a 0 and a k. These three.
Sir, what are those k, 0 and k?
Come again?
So what are those minus k, 0 and k?
Those are R1 minus R2 needs to take these values in order for our prefix, our subarray to be divisible by k.
Okay.
Others? If you understand, can you acknowledge? And if you don't, can you ask questions? So this is part B of the question. So now I told, so what have I done? Let's go back. We have done part A, wherein we said that the total subarrays is basically nothing but ending at 1 plus ending at 2 plus ending at 3 and so on. And then in part B, I saw that ending at a particular j, the property is that the total sum modulo k minus the current SI, that prefix array modulo k, this has to be either minus k or 0 or k, right? This is what I have done in part B. So I have just transformed the property from that of that sub array to a property of the prefix array. So I said that the total number of sub arrays which are or whose sum is divisible by k is equivalent to the total number of prefix arrays that satisfy this property. What is the property? The property is that the total sum till j modulo k minus the sum of that prefix array modulo k is either minus k or 0 or k. So that is part B. So once
Sir,
I know this, yeah.
sir, in the second condition, instead of minus k, 0 and k, we have three values, right? If we take modulo another time, it would just reduce to 0.
Yeah. So basically you can, I'll come to that alternate approach. When you take, so what you can do is you can convert the remainder to positive always. We will see that. Just let's finish this first. Okay. Is that what you're trying to say, Pranav?
Yeah, yes, sir.
Yeah. So we will come to that. So this is part B. Now, once I know this, now basically at a given j, I have to find all prefix arrays with this property. So now searching for across all prefix arrays can be done using hash tables. So how? So for every prefix array, if I store the remainder that I get, right? So for every prefix array, if I store the count, so for remainder R1, I can store count C1. So basically this entry in the hash table contains the total number of prefix arrays with whose sum modulo k is R1, right? So now I can store that in a prefix array so that when I am at a particular j, I can easily find, so I will find out this remainder. So because I know the cumulative sum till j, so let's say that is S. So I can find out S modulo k. Let's call this R. So once I find out this R, I just need to, so then in the prefix array, what do I have to find? I have to find this plus k. So I have to find R plus k, R and R minus k, right? So I've just substituted R here in this expression and I have found out this. So I have to find prefix arrays with this remainders. So I can just sum up, let's say this was C, Cj, Ck and Cl. So this is the total answer for ending at j. And then I can move to j plus 1. So this is how I optimize the search. So my searching now is in constant time. Let's see the code and then we can take more questions if you don't understand anything. So first things first, this is the size and I will need an unordered map or a hash table to store the prefix, the remainder and the count, right? So both of them will be integers. Let's call it M. And to account for the empty prefix array, I will have to do an entry as I did yesterday also. So what is the remainder? The remainder is 0, right? And there is one prefix array, which is the empty prefix array. And then I can go over all the elements. And I will have a cumulative sum. So this is the cumulative sum. Now let's do R. Let's find R. So R is nothing but cumulative sum modulo K, right? So now I have to, and let's take the result. So basically I will sum M of R minus K, then M of R plus K, and then M of R. And finally I will put it in the hash table also, whatever current remainder is, M of R plus plus. And finally I can just return this result. So this is the code. Now you can ask me questions on this code if you want, if anything is not clear. Yes, I can do a dry run. Okay, other than that, let's take this example itself and let's do a dry run on this example itself. Okay. So what is the array? The array is 4, 5, 0, -2, -3, and 1. So let's see, when I begin, I is 0. So my map is just containing this, that there is one prefix array, which is the empty prefix array, which has a remainder of 0. That's what is conveyed through this line of code. Now I start, so first I start with 4. So the sum becomes 4, and 4 modulo 5 is 4, right? So now I am looking for 4 minus 5, which is -1, 4 plus 5, which is 9, and 4. So all the three are 0 in the map, right? I don't have a -1, I don't have a 9, I don't have a 4. I only have a 0, right? So this result is still remains 0. Now in this line, I append this to the map. So basically now I know that I have encountered one prefix array with sum 4, with remainder 4 on dividing it with 5, right? So I do this. Now I move on and I am here. So my result is now still 0. Okay. So result is still 0. Now I am here. The cumulative sum is 9. 9 modulo 5 is 4 again. So now I am looking for 4 minus 5, which is -1, 4, and 4 plus 5. So 4 minus 5, which is -1, I don't have anything in the map. 4, I have 1. So my result increments by 1. And 4 plus 5, I don't have anything. So I am good. So my total result becomes 1. And what is the meaning of that? The meaning of that is that this entire thing, this thing took a remainder of 4, and this thing gave a remainder, this entire thing gives a remainder of 4, as well as this thing gives a remainder of 4. So this thing gives a remainder of 0 on dividing by 5. So that's the intuition. So now result becomes 1. And now I will append this to the map. So basically 4, again I will increment the count by 2. So basically I have encountered two prefixes. This is one prefix array and this is another prefix array which I have encountered. Both of them leave a remainder of 4 on dividing by 5. So I have a count of 2 now. Now I am here. So the cumulative sum is 9 again. So when it is 9 modulo 5, it is again 4. So 4 minus 5, 4 plus 5, and 4. So 4 minus 5 is -1, I don't have anything. 4 plus 5 is 9, I don't have anything. 4, I have 2. So I will increment this by 2. So this becomes 3 now. And then in the map, I will say that. So this becomes 3 now. Now I move on. Now I am here. So the cumulative sum is 7. So 7 modulo 5 is 2, right? So I'm looking for 2 minus 5, which is minus 3, 2, and 2 plus 5, which is 7, right? So 2 minus 5 I don't have, 2 also I don't have, and 2 plus 5 also I don't have. So result is not affected. Now I basically add that 2 also. So basically now I have encountered one prefix array with sum 2. So I am done till here. Let's move on. So now I am here. So basically now the sum is 4 again. So for 4 again you will look at 4 modulo 5 is again 4. So for 4 again you will look at 4 minus 1 and 5 and 9, right? So 4 you have 3, minus 1 you don't have anything, 9 you don't have anything. So 3 plus 3 becomes 6, and you append 4 again, so this becomes 4. And then you move on. Now this is the array. So now you have 5. 5 modulo 5 is 0. So you are looking for minus 5, 0, and plus 5. So you don't have anything. Minus 5 you don't have, 0 you have 1. So you will add it here. And plus 5 you don't have anything. So you are good. And you will increment it this by 2, and you are done. So the result is now 7, and 7 is the answer. Did you follow, Sai? Yeah, I mean, dry run helps, but just look at the abstract idea, how we are doing it. If you understand the abstract idea and if you're consistent with it throughout, then you can be sure that this will work. Any more questions on this? If it is clear, can I have an acknowledgement? On this type of problem, this will keep haunting you again and again. This will keep coming back to you. So this is a pattern that subarrays is something that will keep coming back, and I will show you countless occasions when we use this pattern, this view, as well as optimizing the search using a map. Ankit, is it clear? Ashirwad, is it clear? Divya, are you following? Mantavya, hi, long time no talk. Are you following? Pravalika, long time no talk. Okay. So this is one way of doing it. The other way of doing it, now here basically I took into account negative remainders also. Can I do it in a more simpler manner, wherein I convert the negative remainders also into a positive remainder? So if I have only positive remainders, then I know the math, right? The math is only only 0, right? So I am R1 equals R2 is the math for positive remainders, right? We did that. So can I make this remainder positive always? Yeah, so I can do that. So what I will do is, if this becomes negative, then can I add k to it? Now it becomes positive. So then I don't need these two cases. And this will also give me the same result.
So how
Yeah,
would
Karan.
adding the remainder k fix the problem? I couldn't grasp that.
Yeah, so basically we are just looking for positive. So you understand that this is still a valid division, right? So minus 50, minus 17 if you are writing, or minus 12 you are writing, you can still write it as minus 3 into 5 plus 3, right? Or you could write it as minus 2 into 5 minus 2.
Minus 17.
So I'm saying minus 12, you could write it as,
Minus 12. That's right.
you could write it as minus 3 into, you could, so what C++ does is it does this when you are dividing it by 5.
Okay.
This is one way you could write it. Other way you could write it is the same thing. You could write it as,
Minus.
yeah, this will be minus, that will be plus, this will be minus.
Yeah.
Yeah. So you could
So
write
we'll
it in
take
both
the
the ways.
second option.
Yeah. In C++, basically it gives us this. So if it gives us this, then we have to take the range of remainders as from minus k minus 1 to k minus 1.
K minus 1. Yeah.
And if we convert it to positive, then it is always 0 to k minus 1. So if it is 0
Yeah.
to k minus 1, then we did the math, right? That the difference is always like, there has to be equal. So then it is consistent with
Understood. Understood.
yeah, we are just making sure that.
Okay. So would there be questions of the same variety also? Because these are, I feel, the toughest questions out there. One of the toughest, because it's a pattern that keeps repeating.
Yeah, I mean, there are a lot of questions which come like, so we will today itself we will do another question wherein we will need an ordered map for this, for the same type of question basically. So this view of the subarray really helps, that you are basically taking a subarray as the total prefix array minus a prefix array before j, right? You were there, right, in the beginning of the class today?
Yeah.
Or,
I understand.
yeah. So that view helps. We will do more questions and you will become more comfortable. But yeah, this is a pattern that occurs frequently. So I thought it is worthwhile
Okay,
to
sir.
discuss this.
Okay.
All right. Shall we move on? All good so far? You are following?
Sir, why C++ takes only that minus wala part?
So why it takes as in, so C++ का फंडा ये होता है कि what it does is it is, so that modulo is not a strict modulo. So see, by definition, see, there are two things here that we are talking about. We are talking about modulo and we are talking about remainder. So in an ideal world, both are different. This is not equals to this. So remainder is basically what you understand. When you divide a number by another number, the thing that remains is the remainder. Correct. So when you divide minus 12 by 5, the remainder that you get is minus 2. Modulo is something else. Modulo is not truly equals to remainder. So C++ misleads in the sense that it calls it A modulo B, but this is actually A rem B, A remainder B. So modulos are strictly positive. Modulos always are strictly positive. So for instance, if you say Python, in Python, if you do A modulo B, it is strictly, it ensures that the A modulo B is in the range 0 to B minus 1. But C++ treats A modulo B as A remainder B. And if it is A remainder B, then it can take a range, a negative value as well. So we can like discuss this later, the difference between modulo and remainder. It will just like take up another 15-20 minutes of our time. So yeah, let's discuss it after the class. What is the difference, actual difference, if you are not aware of it?
Okay, sir.
Okay, modulo is basically cyclic. It's just a cyclic property that you ensure. And remainder is proper factor remainder theorem, the division that you do, old school division that you do. Let's talk about it after the class, okay? Okay, if this is clear, let's do, so I will give you a couple of questions. You try it at home and then we can discuss it tomorrow. Those are also good questions. I thought of doing them in the class, but yeah, let's do it this way that you can try it and then we can come back and revisit them. Okay, so let's do a couple of data structure design questions before we move on to binary search trees. So I'll just summarize what we have done so far. So we have covered what I'm saying, we have covered hash tables in detail. So we looked at the USP of hash tables, what USP it offers, like why it is so pervasive in the industry, why people talk about it so much. Then we looked at how it achieves that USP, which is basically the implementation, how it achieves the USP. And then finally, we looked at some applications wherein the types of problems that that necessitate the use of a hash table and the problems that can be solved using it. Okay, so this is what we have done so far in the 2.5 days or 2 days and maybe 20% of today's class. So now what we intend to do is, now we will do some basic data structure design. So basically you have some, so the premise of this is that you have some primitive data structures that are known to you, right? You know data structures like arrays, you know linked lists, you know stacks, you know queues, you know hash tables now, right? So these are the data structures that you know. Any other data structure that you know? Not yet, right? You don't know trees now. Let's not go there. So what we will do is, in data structure design, basically we will take up problems wherein we have to design some complicated data structures. So these complicated data structures will warrant something. So we have to design these complicated data structures using these primitive data structures as building blocks. So that's basically the goal. Okay, so we will do questions of this type. So designs, now when we are designing complicated data structures using them as building blocks, then there is no one right answer, right? So this will be like, I expect you guys to give me as innovative and creative solutions as you can. Think about any kind of possibility wherein you can mix and match these in order to arrive at a solution for this complicated data structure. So these are design problems. They will be a lot of fun. So we will do that now. And then towards the end, what we will do is we will motivate the need for BSTs if time permits. And we will say that why we, even though we have a hash table, why we need a BST. And from there, then we will again talk about these 3 things for BST. But that's after this. So this is what we are doing now. Okay, all good. So let's start. This will be fun. So, I mean, at least I like it. Let's start with a very simple question, a question that you got in the hackathon as well. But let's try this first. I will tell you the number. So this is question number 155. This is a very, like, this was given in the hackathon also, if you guys happen to participate in it. But read this question. This is a design question. So how would you do this? So the question is that you know about a stack, right? You know a general stack and the types of operations that it supports. that you have elements in the stack, you can retrieve the top of the stack. So stack is nothing but a last in first out structure, right? So you can basically retrieve the top element in order one time, which is basically the last element or the most recent element, and then you can delete it as well. So you can pop it out, as well as you can push one and you can retrieve the top. What you have to do is, in this question, you have to design a min stack. So in min stack, you don't have to when you retrieve an element, you don't have to retrieve the topmost element. So what is the definition of top in a conventional stack? In a conventional stack, you are talking about the most recent element, right? That's the last in first out principle. So now you have to design a stack wherein you don't have to retrieve the most recent element, but you need to retrieve the minimum element. So the s dot top should give you the minimum element in order one time. And of course, you should be able to support push and pop, which is pushing a random element into the stack and popping it out, popping a random element, popping the, so what is popping? Popping is basically, so actually this is, there is a difference here. So you have to basically support additional, apart from push, pop and top of a conventional stack. So push, pop and top will basically return the same result as this. Apart from that, you have to return support a get min, which should return the minimum elements encountered so far, but that also should be in order one. How would you do this?
So we will use two stacks here.
You will use two stacks. Okay.
So then we will simultaneously compare, one will be the general normal stack and another will be the minimum stack. And then we will iterate accordingly. We will check through the elements and we see that if the top element of the stack is if the element that we are currently right now is smaller than the one which is on the current stack, on the top of the current stack, they will push it to the minimum stack. And simultaneously we will do certain similar comparisons and we'll do the push and pop operations in similar manner. We can do the operations in O1.
Yeah, so basically the idea is, you're right. So basically the idea is that what we can do is, I can keep two stacks. One is the normal stack and I can keep a min stack. So what this does is, this keeps the minimum that I have encountered so far as the top element. This is the normal stack, right? I can do that. How can I do that? So whenever a random element comes in the normal stack, I can just push it. It's fine, right? How will I ensure that after I push this element in the min stack, this the top of this will contain the minimum of all the elements that I have encountered so far? Whatever was the top so far, I can compare that with the element that is coming in, right? And I can push the minimum of those two here, right? So whatever was the top of the stack is actually the minimum of all the elements which I have encountered so far, excluding this element that is coming in, right? So this element, if it is smaller than that top, then basically this becomes the new minimum for the entire stack. Otherwise, the whatever was the previous minimum still remains the minimum for the entire stack, including this element, right? So I can push the minimum of these two values as the new element. And in the normal stack, I can just push the new element. So then basically in push, I can do S1 dot push and S2 dot push minimum of the element and S2 dot top, right? In pop, I can simply pop S1 dot pop. In top, I can give you S1 dot top. And in get min, I can give you S2 dot top, right? So let's see the code very quickly. We will things will become very start going over your head in half an hour. Don't worry. We will level up very quickly. So let's see this. So what will I do? I'm thinking of keeping two stacks. Both will be integers if we are keeping integers. So this is basically the normal stack. And let's keep another one, which is the main stack. So when I'm pushing, I can simply push X, and in main stack, I can push minimum of X and min stack dot top. But I just need to take care of the case when min stack is empty. So that you can take care of. If min stack is empty, then you can simply push X. Otherwise, you can basically push the minimum. Then pop is nothing but S dot pop and min stack dot pop. Top is S dot top. Get min is min stack dot top. Okay, is this clear to everyone?
Sir, could you repeat that on whiteboard again?
Uh,
The previous one.
the min stack.
Yes, sir.
So just do a dry run on what we are doing. Let's do a dry run if you don't understand. So what are we doing? We are keeping two stacks. So what we are doing is we are keeping two stacks. One we calling S and one we are calling main stack. Let's take elements as and when they come. Let's say we are taking 5, 7, 2, 3, 11, 15, 4. So let's say these are the elements that are coming in. So when 5 comes in, I will simply push 5 to both the stacks. Okay. Now when 7 comes in, I will simply push 7 in this stack. So this is the normal stack. So I'll just push 7. Now in this main stack, what I will do is I will compare this with the top. So out of these two, whichever is the minimum, I will push. So I will push 5 here, which is basically the minimum of 5 and 7. So basically this, the top of this stack stores the minimum of this. Okay. So now when I get 2, I will push 2 here. This is the normal one. Here I will push the minimum of 2 and whatever is the minimum so far. So the minimum so far is the top, which is 5. And I will push the minimum of this and the minimum so far, which is 5. So minimum of 2 and 5, which is 2. So now basically this top stores the minimum of this. So I'm getting the minimum also running minimum stored in the stack. So now when I get
Okay.
3, I will just push 3. Here I will push 2 again. Then 2 and 3 minimum is 2. 11 I will just push here. I will push 2 here again. 15 also I will push 2 here. I will push 15 here. 4 again I will push 2 and 4 here. Then now I can pop both or the return the minimum. Right? Is it clear to
Okay,
everyone? People who have not seen this question anytime? Clear? No issues in understanding this, right? Let's level up a little bit and let's try this question. Like by the end of today's or tomorrow's class, we'll be doing all hard questions. So let's try this. This is, I will tell you the number. This is 981. So tell me, how do you go about? These are all design questions, so I expect a lot of interaction. I mean, you can brainstorm ideas, whatever ideas come to your mind. So do you understand the question first? So what is the question telling you? The question is telling you that we know about ordinary key value stores, right? Which is what we have been doing in ordered unordered maps. Also, we were basically storing key values, key value pairs, right? Here we have to design a time-based key value store. So what that basically means is that every time you get a key value, so every time you get a key value and a timestamp, which you store it in the container. So for the same key and value, you can get multiple with different timestamps. So you can get key 3, value 2, and timestamp 1. So this was, and then you can get key 3, value 2 at timestamp 5 again. And then basically what you have to do is you have to retrieve the, at any point you can be given a key and a timestamp. You have to retrieve that key which occurred most recently compared to that timestamp. So if you get a query of let's say 3,4, you have to retrieve an entry from this container with key 3 and with a timestamp less equals 4. The most recent timestamp less equals 4. So in this case, it will be this. You have to give out this as the answer.
So we can make a map.
What map?
Like, we can create like a ordered map where we can create the key, and along with that, let's say, and another two like the timestamp and the value, we can set them as pair. So corresponding to that, we can perform.
Okay, but what will you do with that? So you are saying we can have a map.
So like we will compare for the same key values if we get the time, if we have any timestamp which is just less than or equal to k, then we will just give out, like we will give out the uh, like the other string as the like as the result.
Can we use a stack to store the minimum key timestamps?
Minimum timestamp to store in a stack.
Not minimum timestamp, but the key value of the minimum timestamp. Suppose timestamp is 3 and the key value for that is 2. We will store the 2 in the stack.
But how many stacks will you have? For every key, you will have a stack.
We'll just, as we done in the previous problem, we'll just update the minimum
You will just update the minimum is fine, but you have to retrieve for a given key, right? For a given key, you will have to
Yes.
retrieve the pair with the most recent timestamp. Retrieve the value with the timestamp with the largest timestamp less equals that timestamp, the given timestamp,
Okay.
right? So for that key, you have to retrieve, not generally anything. Otherwise, it will be the most recent entry always, like the most recent entry just before that time that you are given. Think a little more.
Mm.
So one thing is, let's see some patterns. Drishan is asking, can we combine the key and timestamp into one value? You can keep pairs. You have pairs. That should be fine. But that's not the. So see, one thing is you have to keep all the tuples, not the tuples, but all the three tuple. You have to keep all the key value timestamps in this container, right? You cannot optimize by removing anything. Why? Because you could get any random timestamp tj, and you basically will have to retrieve for any given key, you have to retrieve any such entry, right? So you cannot optimize by removing anything. You have to keep all these. That's one thing that I think will be there, right? So first things first, let's see. You have two things that you want to insert. So you want to do insertion on efficiently, and then you have to do a get efficiently, correct? So insert is basically set in this case. So one thing is sure, for insertion we have to use a map, right? Because that's the only way we can insert efficiently, right? So first thing that will come to my mind is, okay, let me keep a map. So for insertion, I will have to use a map. So I will have to use a map with key as the index, right? With a key as the mapping. The next thing that comes to my mind is the same key, I can have multiple VITI pairs, right? So basically for a given key, I need to have some complicated data structure here to store all these tuples, value V1, T1, V2, T2, V3, T3, right? So let's see what can we do. So can I keep a map
Can we?
with value as an array? So basically for this key1 K1, key K1, you will store all the value timestamp pairs, V1, T1, V2, T2, V3, T3, V4, T4. So as they are coming, you will keep appending at the back. So as they are coming, one thing is sure, that these will be in increasing timestamp, increasing order of timestamp, right? Why? Because they are coming at the future time. You don't need to sort it. That's what I'm trying to say. This entry will be populated after you populate this entry, right? So, and these entries are coming in a chronological order. So anything that you encounter to the right of something will have a timestamp greater if you are just appending elements as and when they are coming, right? This part is clear to everyone? I can repeat if it is not clear. Please feel free to speak up. So then basically, whenever I get a key value timestamp pair, I can simply go to the correct appropriate location in the map, and I know I have an array, so I can just push that value VITI here. That is the set operation. And then the get operation is, So get operation, I will have a key and a timestamp, right? TJ. So I can just go to that particular location using by the key. And then in that array, can I do binary search to find that timestamp, the greatest timestamp less equals TJ? I can do binary search and get it. Correct? So this is insertion will be order 1 and get will be order of log of the size of this array, whatever. Right? Is this a good design? Do you, first of all, do you understand this design? First things first, do you understand how we arrived at this design? What are the things that we looked at here? We looked at the point that we have to insert using keys. So we have to have a map. Yes, Ravan, I can explain. See, you have to, in any case, you have to insert using whatever operations you are doing doing with the help of a key. So anything that you are searching is with the help of a key, right? You are inserting with the help of a key, you are retrieving with the help of a key. So you definitely need to have a map with this key as the key. That is for sure. That's the first observation that I did. The second observation that I'm doing here is that I am seeing that for the same key, I can have multiple VITI pairs. So it's possible. So definitely this particular value of this key cannot be a primitive type or a pair. It has to be some other data structure, right? So then I just did a trial, hit and try. So I said, let's try array and let's see, can an array help? So then I said that let me keep the value of this as an array, and that array will be, every element of that array is a pair. So I am storing VITI pairs. So now the third observation that I will do here is, so I just did two observations, that I just necessitated the need of a map. And then the second part I told you is, I told you that the need for the value to be a data structure, value of map to be a data structure. So now I just said, let's try an array. We will see complicated data structures, but let's try an array. So then the third part that I'm looking at is that the get operation. So I need to optimize the get operation, which is basically for a given key in that array, I need to search for a certain timestamp, right? So naturally the thing that comes to my mind is, can I keep a sorted array so that my searching is log n or binary search is applicable?
Sir, I have a small doubt.
Yeah.
If you want to make search to be login and the array to be sorted, then the insert won't be order 1, right? Because then when we are inserting, we'll have to insert and then resort.
No, so that's what that's the beauty of this question. Here insert will be order 1, which is what I am coming to. So see, I just necessitated the use of a sorted array. Now let's see how can I keep this array sorted. So one thing is for sure, for a given key, if I have VI, if I have a pair VITI, and for the same key, if I have a pair VJTJ, and I know that this came in later than this, then I definitely know that TJ is greater than TI, right? Because these are timestamps. So I can just put to the append at the back of the array. So I will definitely, I know that whatever I am getting here will have a timestamp greater than all these timestamps, because this has arrived after all these arrived in the insertion process, right? And I'm not deleting anything, first of all.
Okay, so the timestamps are necessarily will be in increasing order.
Yeah,
at least non-decreasing order.
Yeah, timestamp will be non-decreasing because that's the meaning of timestamp, right?
Okay, yeah.
Yeah. Correct. So I can append in order 1 and then I can have a sorted array. Then I can search in log n. So that's basically the idea. these three observations led me to arrive at this data structure, that is this DS design. Does that make sense, Raman?
Sir, that array contains value and time, right?
Yeah, value and time.
Then how we do binary search on both?
You can just search
Uh,
on time, right?
only time.
Yeah, yeah, yeah.
Okay,
We
then
will do it. You will see.
like how two values are stored in array here?
You can have a pair, right?
Okay,
If you are
okay,
talking about an implementation perspective, you can have a pair,
okay.
or you can have a vector also of size 2. It really doesn't matter. Karan has a good question. Karan is asking, can we have a hash table inside a hash table? So the question that Karan is asking is that, okay, we saw that for a particular key, I need a complicated data structure. We tried arrays and it works. Can we have another hash table here? You can have a hash table, but how will you search in this hash table? So if you see here, what you have to do is you have to, so this hash table will obviously the key will be timestamp, right? That is natural because you have to search for timestamps, search on the basis of timestamps, right, Karan? That is the first observation. So this hash table, the key will be timestamp. That is fine. But what you have to search is not an exact timestamp, right? You have to search for the greatest timestamp, which is less equals the t that you are given. So in hash table, there is no efficient way of doing that. So you will have to traverse the entire hash table for that, which will typically take order n. And that's why we can, like, it is inefficient to use a hash table here. Did you get this point? So think about the searching. You have to search. What do you have to search in the get operation? In the get operation, for a given key, you have to, and a given timestamp t, you have to search for, so in this key, you have to search for an entry in this hash table, the largest such timestamp, which is less equals t, right? You have to search for that. You don't have to search for exactly t in this hash table. So even if you keep the key as a timestamp, you will not be able to do m of t, right? That is not right. That will not give you the answer. You will have to iterate through the hash table to get that. And that iteration is order n. So what you can do, so that's why hash tables are called unordered search structures. So underlying, they don't have any ordering of the keys. So hash tables are basically what? They are key value pairs, right? So hash tables don't have any ordering of the keys. They are just there. But we will look at ordered search structures today, which are basically binary search trees implemented using binary search trees, wherein the keys are ordered. So then if the keys are ordered, then this searching for this kind of a property becomes efficient in that kind of a data structure. So this, you can keep a map, but you will have to keep an ordered map for people who know ordered maps. But if you don't know, don't worry, we will come back to this question when we talk about ordered maps. I think you did not understand, Karan, this last point, which is fine. We will come back to it. Don't worry about it. Okay. Vidyut, can we use val in second hash table? What do you mean val in second hash table? Whatever it is, the second hash table, why do you want to use value as the key? How will that help? So whatever key you should use should be to facilitate the searching. Here you have to search for timestamps. Once you have done the first level of searching, wherein you have narrowed down on a key, you have to search for a timestamp. Correct? So you cannot. Cool. Shall we implement this? Let's quickly implement this. Just follow the syntax. So let's see. So we said that we will keep an unordered map with the key as a string, key as the key, and the value will be a vector. And what will be the vector? The vector will be a pair of timestamp and the value. So timestamp is int and value is key. So I can keep pair of int and string. So this is what we said we will keep. Now when we set it, what you have to do is you have to go to that key. So now you have gone to that key. So m of key is a value. What is the value? The value is a vector, correct? So the value is a vector. What you will do, you have to push back. What do you have to push back? You have to push back the value and the timestamp. So that is a pair. Every element of the vector is a pair. So you have to push back a pair. So you can make a pair now. And make a pair of timestamp, comma value. And this is the basically the set operation. This is order one. Set operation is clear to you? Any questions on the set operation? If you have, ask me. Otherwise, get is even more involved. Clear, right? Everyone understands this. M of key is a value. Value is the vector. So we push in the vector. What do we push? We push this. So how do we create this? Using this make pair and the same order, int string. So it is timestamp and value. So let's do a get. So get is basically you have to find let's say you have to do a find key. And what do you have to find? What is the array? The array is m of key. So you have to find in this array for this timestamp, correct? So let's just do a return here. We will write the function here. So let's do a string find key. We have a vector. What is the vector? We have a vector which is a pair of int and string. This is again I'm passing as reference, mind you. And I have a timestamp. Let's call it TS. So I have to basically find the largest pair in V with T less equals timestamp. This is what I have to do. So now we will do binary search. So brace yourselves. So my low is 0. Predicate, right? I will just do it. Make sure you understand. If you don't, ask me. So high is this, mid is this. I will just do while low less than high. I am doing an F star T star. I don't know whether you remember this or not. I don't remember, but I'm still trying to. I have to, if I'm doing an F star T star, what predicate should I use? I should use P of X. So basically V of I need it to be false. And I have to find the, so I have to find the largest, right? So that largest should either be the beginning or the last F. So it cannot be the first t, right? Because yeah, it cannot. I think we have done this. It cannot be the first t. It will be the last f. So then basically I'm saying that Vx greater than Ts. This is the predicate. And I have to find the last f. So let's find the last f. I don't know the mid calculation now. We will come back to how to calculate whether it's a low mid or a high mid. But the predicate is that if V of mid is greater than Ts, so this is true. So if I'm in the true part, I can skip it because I have to find the last f. Otherwise, I cannot skip the f. So this will be the low. And now I can say that my mid will be a high mid. It will be dictated by this. Right? So it will be low plus high minus low plus 1 by 2. And now I will do the sanity check, which is the final one, that if so these you have to just take care. If V of mid dot first, because it's a pair, so V mid dot first will give you the timestamp. So I'm just comparing on the basis of the timestamp. And finally, if V of low dot first, so this is basically what is remaining. If it is true, if it is still greater than timestamp, then you should return empty string. It is given there. Otherwise, you should return V of low dot second. Is this correct? I don't know how many of you followed with me, but if you remember some parts of binary search lecture, we have just done that. So this is basically order log, let's just say n. It's not exactly n, it's just for that key how many values we have. Now you can ask me questions. I will just take a pause. So you can stare at this code and ask me questions.
Sir, you said we are storing in increasing timestamp, right? So where we are doing that operation?
That is inherently there. When I'm pushing back, I know that the next pair that I'm getting will have a timestamp which will be greater than any of the pairs that I have already pushed in this array. Why? Because they are timestamps. So anything that I get later will have a greater timestamp than anything that I get earlier. It's given also.
Okay.
If you don't
Okay.
understand. So you can see this timestamp for set operations are strictly increasing. It's given also. Is this clear to everyone? Can I have acknowledgements before we move on to the next data structure? Okay. Let's do another. Let's do this first. I mean, I can give you a harder question, but let's do this first. That will be difficult than this. Let's do this. So this is 380. So what's going on in your head when you see this question? Like, what is the difficulty in this question inherently? Why is this a difficult question? Because of the get random, right? I mean, insert and delete are fine. You can just use a hash table, right? What is the difficulty here? The difficulty is that you have to get a random element from all the elements that you have inserted with equal probability.
So, would the removal be supported in O of 1?
Would the removal be supported in O of 1? I mean, ideally they want it to be O of 1. Yes. I mean, the design that we will do the eventual solution, it will have
Average.
O of 1. Average, yeah. Yeah, but it's okay. The final solution that we will do will have O of 1 in all the three average case. So see, the problem here in this question is just the random, get random. That is just making this problem unnecessarily hard. Why? See, you can insert delete in a map, right? So what is the question? The question is you are giving, you elements are coming in, you have to insert them as well as delete them. And at any point you can get a call to get random. So you should return an element from the container with equal probability, whatever elements are there in the container. So using a hash map is obviously necessary. Why? Because you have to insert and delete, right? So insert and delete, if you want to do in order one time, there is no other data structure other than a hash map. So definitely a hash map is needed. That's the first observation. So you cannot get away without a hash table. So you need a hash table, definitely. That's the first part. But now, do we need more? We will need more than a hash table. Why? Because this hash table is fine. But the third operation, which is get random, how will you do in a hash table? You cannot. So typically, what is get random? I'll just give you some intuition around get random. So you have some numbers which you already have gotten so far. Let's say 14, 5. You have to pick an element from these numbers randomly with equal probability. What is an order one way of doing it? An order one way of doing it is you arrange them in an order. So put them in a line. So let's say you put 23, 25, 27, 14 and 5. Put them in a line, give them positions. Once you have positions for them, then what you can do is positions from a given range. So now you have a positions from 0 to 5. 5 is open. So now what you can do is you can pick a position randomly, right? And then return the corresponding element. So picking a position randomly from a range is order 1. Correct? Do you understand this part? So size of the hash table will not help with you. That's what I'm saying. How will you know if you size of hash table you can return in order one time? That is fine. You just do an m.size that will give you the size, and this is order 1 only. But now if you generate a random number between 0 to m.size minus 1, how will you know which element is there? Like you don't have indexes, right? The sizes are not the indexes in this hash table. So to find the kth element in the hash table, you will have to iterate through the hash table till k. So that will be order k time to get a random element. Do you see what I'm saying, Vidyut? Yes, so that is not order one. Table dot begin plus random number is not order one. That is order random number for a map. It is not random. It is constant for arrays because arrays are contiguous in memory. In hash table, this is not constant. Searching is on a key in a hash table, not on a position. On a position, you will have to iterate and do the hard work. Do you people, are you understanding what Vidyut asked? It's a very legit question which will come in all of our minds. Like, do you understand what he asked and why it does not work? Yeah. So others, Divya, do you understand? Assuming you are there. Ashirwad, Ashray, are you following? Awake, alive? Mantavya, I haven't heard your voice for like in 2020. Simran is also here today. Hi Simran, it's been a long time. Right. So the only thing, so now what I need is I need an, so I can get a random integer in a range. Okay, that is in order one, but I need to find that corresponding element in order one. So what is the data structure for that? There is only one data structure that allows us to access elements randomly. Array, right? So you need an array. That's the second observation. From that range, so you can put, so you will need to put the same elements in an array also. Correct? So now think, so now this is fine. Now let's see how we will do these operations, all the three operations that they are talking about. So let's talk about insert. So insert, I can insert in an hash table. So this will be order one. In an array, I can only insert in order one if I push back. Correct? So let's push back. We will come back and revise this if needed. But for now, let's just push back because that is the only way we can insert in order one. Otherwise, it will take time because you will have to replace elements like yeah, you will have to transfer elements to the right or left depending on where you are inserting it. So that's insert for you. Let's talk about get random. Then we'll talk about delete. So get random, what you will do, you can just generate an index from 0 to a dot size, where a is the size of the array, a dot size minus 1. You can just generate a random number in this range, and then you can return a of that random. Correct? This will give you the number in order one time. So you have solved the get random problem through this. Right? Let's talk about delete. So delete in a hash table, I can do in order one. Obviously, that's what hash tables are built for. I can just do an erase. I will be able to delete in order one. Now comes the trickier part of deleting from an array. So what is deleting from an array?
So on average, wouldn't the deletion part be O of log n in hash tables because they're implemented as a binary search tree?
Unordered maps we will use, those are hash tables. Ordered maps are binary search trees. So we have only discussed unordered maps so far. So unordered maps are all order one average because underneath they are implemented as hash tables. Ordered maps are implemented as binary search trees. So there you will have a complexity of log n.
Okay.
Swap with the last element and then pop back. Yes, that's the idea. But first things first, how will you find that element in that array? You will have to find it, right?
What's the question you asked?
The
Like
question
delete.
is, how do you delete from the array in order one? There are two steps in this deletion, right? You have to first locate that element. You have to locate that element in order one, and then you have to remove it also in order one. Now, both of these are hard tasks in arrays. Now think. Location, I guess you guys got it. I like both of them, you got it. So how do you locate in the array in constant time? You can come back from the map, right? From in the table, you can store the index where you are putting it in the array, so that you can do an m of that v dot second, let's say, dot value. So m of v will give you the position in the array where you are stored it. So that way you can locate it in order one time. Correct? Do you understand this? Everyone understands this? How do you remove this? Just understand this, that in this array, there is no ordering as such. So what you can do is, you can simply, so once you have located this element that you want to delete, how did you locate it? You located it from the table. So from the table, the value of that table, for that key was the index in the array where you are storing that element. So once you have located that, what you can do is you can simply swap it with the last element and then remove the last element. But of course, so the only thing that you will need to take care of is when you are swapping it, you will need to adjust for this element. You will have to adjust the entry in the map, because in the map, the entry would have been for this index. Now you have to change it to this index. Now ask me questions. I can repeat this deletion part again. If I went too fast.
Sir, why we are swapping here?
How will you delete in order one in an array if you don't swap? You will have to otherwise shift elements.
Okay,
Shifting
okay,
will not be
okay,
order
okay.
one, right?
Yes, sir, got it.
Is this clear? Not clear? Ask me questions if any part of this is not clear. If I went too fast in the delete part, I can repeat any aspect of this delete. If you want me to take an example, we can take an example also. Just write on the chat whatever you want. I am just taking a pause of 30 seconds or so. Yeah, let's see. What does the map contain? So Karan, the map will contain, so the map is basically, the key will be the element that is coming in. So the key will be that. So key is the element that's coming in, and the value will be the index in the array, index of the array where the element is stored. This will be in the map, and in the array you will just have the key, the elements. So let's say for ELT3, so for ELT3, the key will be ELT3 and the value will be 0, 1, 2. So the value will be 2. For ELT1, you will have 0. So then the deletion is basically, you just go to that element, go to the value of that element. This is order one, right? You can go to the value from the key in order one. That's the USP of a hash table. So once you go, you know the index. So now from here, you can go to the corresponding index. So now you have to remove this element. So from here to here is also constant time, right? Because arrays are randomly, you can access any element of the array randomly. So now once you know the index, you can straight away go to that element in order one time. That's the USP of arrays. We're just using USPs of each of these data structures, if you take a look at it closely. So now we are here. So now we want to remove this. So one best way of removing it is that you can swap it with this element and you can remove this element. So this removal is order one, Bidyut. Why? Because you just have to reduce the size by 1, the size variable by 1.
So we are swapping the elements, right?
Mhm.
Okay.
So we are swapping the element. Swapping is also constant time, right? The only thing that we will need to take care of is that this ELTN that you swapped with. So for this ELTN entry in the hash table, you previously had n minus 1. Now when you swapped it, this ELTN comes here. So you just need to make sure that you update this n minus 1 to 1, like wherever the new index after swapping. So that's also one of the things that you will have to take care of when you are swapping.
Sorry, could you repeat?
So this element, new element that is coming in at this index
Okay.
of the old element. So for that element, the entry in the map was n minus 1, right? Previously, because when you inserted it, you populated it with n minus 1. You just have to update that index. Because now the new index where ELTN is stored is 1, right? This index. So you will have to update that here. So that update is also order 1. Why? Because you know the key. From the key, you can go to the map and you know the position. So you can just override the position. Is that clear, Karmaya?
Yeah.
Let's see the code, whatever existing. Yeah, Karan, you will see the code. So there is a C function which will give you the in constant time, the a random number from a range. We will see. Once you see the code, then we can take up questions. Okay. So let's see. So these are all from DSP2 batches. Okay. So first things first, I need a map. So in the map, what do I have? My key is the key that is coming in. So what is the data type of this? The data type of this is an integer. So my key will be an integer. My value is an index. So indexes are also integers. So this is the map that I'm keeping. Other than that, I need an array. So a
So
vector
wouldn't
of,
it be a pair?
why will it be a pair?
Okay, not a,
Right? I just need to store the index.
okay.
That's it. That key is implicit.
Hmm.
Yeah. So, and I need a vector. So what is the data type of the vector? That the data type of the vector is the data type of this, which is an integer. So I have a vector of integer. Now let's insert. So we will do two things. We have to insert in map and we have to insert in vector. Okay, so let's insert in vector first, just because it's simpler. So how do I insert in the vector? I will just push back. So I will just push back this value. That's the insertion in vector. In the map, when I insert, I will do m of this value. I will store the index. What is the index? The index is v of v dot size minus 1, or right, that is the index. Or you could do m dot insert make pair. So when you insert, you can insert both the key value. So you could do this as well. Both are synonymous. Both of them are same. It's just that I like to do this. This is more readable. So inserting is fine. Let's do get random first. So get random first, I will get a integer, a random integer. So let's get a random index. So random index, I can use the rand function of C. As far as I remember, it does not take anything. So it will return a random number. You can take a modulo with v dot size. So this will give me a random integer in the range. This syntax is right? I can, someone just check the documentation and let me know if this is wrong. As far as I remember, this is the syntax. generate a random integer in 0 to v dot size minus 1. So I've just done that, and now I can return the element which is v of random index. This is the get random call. Both these calls are clear, insert and get random.
Sir,
Because now I will write remove.
in insert in map that v dot size minus 1 is like we are inserting from any number, right? From 0 to like.
Yeah. So this is, so the we are storing, what is the value we are storing in the map? That's the index in the array. The index in the array. तो इंडेक्स क्या होगा इस एलिमेंट का जो अभी आपने इंसर्ट किया? लास्ट इंडेक्स होगा ना, क्योंकि आपने पीछे इंसर्ट किया है इसको. तो लास्ट इंडेक्स क्या होगा? v dot size minus 1.
Okay, sir. Okay.
Clear? Both, I'm assuming both are clear. If it isn't, please speak up now, because I will write remove and then that will become a little more complicated. So let's remove an element. So you have to do two things. You have to remove from vector and you have to remove from map. So let's remove from vector first. So in that, the first step is get the location in the vector. So how do you get the location? So that location is m of value, right? Now do the actual act of removal. So remove by swapping. So what you will do is you will swap v of location with v of v dot size minus 1. That's the last element. The third thing that you will do is you update the index of the newly moved in element, the element that has come in at index location. Update the index. So how do you update? First go to the map. So map of v dot location. V dot location will contain the key. Now after swapping, right, the new element will be at vloc. So vloc is the key. So I just go to the map through mvloc and I update this to lock. Previously it was v dot size minus 1, right? And then I simply pop the last element, which is v dot pop back. So this is how we remove from the vector. And removing from the map is easy. You can just erase value. Just look at the return values. Inserts a value to the set, returns true if the set did not already contain the element. Okay, so just do that. So if m dot find value, if it already contains it, then you can just return false. If it does not contain it, you can return true. I'm just doing what it is told. Removes a value. If it does not contain, then you return. So here again, if m dot find value, if it is not found, then just return false from here. Otherwise, go ahead and delete it and then return true. So this is the code, hopefully. Now you can stare at the solution and ask me questions if you have any. This is the most like the tricky part, removal. If you understand all this, please acknowledge and we can move ahead. Why was pair? We are not using pair, Karan, in the map. It's just another way of inserting. This is fine. This is just another way of inserting. Instead of referencing the key by the square bracket, you can do m dot insert the key value. And when you insert the key value, it's just the syntax. You make a pair and insert it. That's how it has been defined in that way, the documentation. The map is still this. The map is not like the key has a pair or a value has a pair. It's just a syntax. Okay, shall we move on? Can you guys acknowledge and we can...
So can you please again tell me like what that random function does? Like, get within.
So what a random function does is it just, so this rand function from C++ library, this gives you a random integer from 0 to some high range, some rand max they have defined, some macro, and it gives you a random integer from that range. So we are just that whatever random number that is giving, we are basically bringing it down to our range by taking a modulo.
So like what is the maximum limit of the random? Like it depends upon what sort of integers we are using, or it has an implicit value?
It has an implicit value. Just check that. It is rand max. They have defined that. That's a macro that they have defined, which has some higher range, like some that you can check.
Yes.
Okay. But if you are interested in the actual act of how it picks a random element, then yes, we can discuss that algorithm. That's also interesting. But that's order one itself. So it's like a...
Like in which, like under which header is it present? Like random. Like if we
check
need to.
check that. I will check it for you. Just see the screen. Let's see. See any of these. See this if you want. So this is, you see, rand max, and the value is at least this much. It depends from implementation to implementation, but this is at least this much, and this is from stdlib. Okay, you can use this. I like this C++ reference. This is better. So this properly, see it, this properly tells you all this. Okay, so the homework for you is the same question modified to allow duplicates as well. So try the same question with duplicates. There is a difficulty in duplicates, which you have to think why this existing solution that we did will not work for duplicates and how you will take care of that. This is 381. So that's the homework. Try that. It's a hard question, but we will discuss it tomorrow. Let's move on to one more final data structure, and then we will do ordered maps or BSTs. This is also a very good question. I like this question for multiple reasons. We will do this maximum frequency stack now. This is 895 of LeetCode. So it's similar to we have to do 895 Karman, you know. So what do I have to do? We have to design a stack wherein which supports pushing. So you can push any number in the stack, and it supports popping. When you pop, it should return the most frequent element. So there are two things here. It should return the most frequent element. That's the first part. The second part of the question is that if there are multiple values with the same frequency, then it should return the most recent, like the value which occurred, which came in the last, or which is the most recent value. So that's how they break ties in this case. So any ideas? It's fine. Space complexity is not really an issue here. You can, yes, ideally the solution that I will be discussing, yes, the space complexity is the same as that of a stack. But for the purposes of this question, it's okay to go above that. Like it will be the same order wise.
Sir, we can use that yesterday's bricks wala question approach, right?
What will you do?
Like we did a question yesterday, right? That bricks wala.
So you will choose
Like
the frequency.
हाँ.
ठीक है, frequency आपने रख लिया, फिर क्या करोगे आप?
तो मैक्सिमम के लिए और एक स्टैक बना लेंगे.
So what are the data structures then? Just
Hash
think
and
about the type breaker also. हाँ ठीक है. Okay, you will have a hash table which is the
stack.
and a stack. Karmanya is saying let's have a hash table and a vector.
Sir, can we use a stack if we are emulating a stack?
Yeah, you can use a traditional stack. That's okay.
Okay.
You can use any of the primitive data structures that we have seen. Yeah. So how do you like, let's see what we have to do here. This is tough. This will take time to digest, but just follow along. Let's see. So
So what if we use a
what if we use?
combination of a hash table, vector, and stack?
Okay.
In the vectors, we keep the unique elements,
Mhm.
and actually,
So there are three
I was
things.
thinking that we
Mhm.
could. Okay, never mind. I think there's one problem with that solution. So let me just go through it completely.
Sure. Okay. So let's think about it. What are the things you have to do? You have to push an element to the stack. That's the first thing that you have to do. The second thing is you have to pop. So you have to return the maximum frequency, the element with the most frequency. That's the first thing. And the second thing is if there are multiple elements with the same frequency, then the tiebreaker is that you have to return the most recent one. This is the question. Now let's see. First things first, a very basic observation is I need to count frequencies of each of the elements, right? Because that is one of the like very basic things that I need. When I retrieve the maximum frequency or when I push an element, I need to count the frequencies, right? That's the basic, like one of the basic requirements that I can observe here. So I need to count the frequencies. So what is one way, possible way you could count frequencies? Just keep an hash table, right? Where the key is the element itself and the value is the frequency. Correct? So whenever you insert, you can simply do m of element plus plus. Right? So that way you will be able to keep a track of the frequency of every element. You need the frequency, obviously. That's the first thing. So now let's talk about the more involved part. Now let's look at this thing. We need to return the element with the maximum frequency. So you can keep an element with, so let's say there was no this 2 was not there, you only had this, and the tiebreaker was that if there are same frequencies, return any one. Let's say this was the question, then this is a very easy question. Why? Because you can return the maximum frequency, but you have to remove also. So that's another thing. Then it becomes difficult. If you don't have to remove, then it's very easy. So if you don't have to remove, you have to just push and return the maximum frequency. You can just count frequencies and keep a variable, right? Which is the maximum frequency. And every time you push an element, you can just update the maximum frequency. And when you have to return the maximum frequency, you can simply return that element, right? That is how you would do it if you just had 1 and 2 ka part 1 without removal. But here you have to, other than returning the maximum frequency, you have to remove that element also. That basically means that you will have to reduce the frequency of that element by 1. So let's see. So the next observation is that I need to store frequencies as well. So I need to retrieve the maximum frequency. So basically I need some data structure which is indexed by frequency, right?
So like we can use a let's say map in this case, like which stores the frequencies itself and it increments by itself.
Come
Like
again.
so at first we created a map where we updated the frequencies of the elements, like how many times it got repeated. And I thought we can create another map where we can store those frequencies and simultaneously we could like update them so that accordingly and that should be in a decreasing order such that we can retrieve the maximum frequency element from the stack and similarly push pop it. So like use it.
So why do you need to use a map? You can keep the maximum frequency. Maximum frequency you can keep using a variable, right? That's not difficult. So the part B is where the problem starts coming in. You need to retrieve the maximum frequency. So my next intuition is, or my next line of thinking is that let me have a data structure which is indexed by frequency, right? That is one way I could go ahead and have a maximum frequency. So
So could we use a map
you could use
with
a
an
map.
inbuilt vector?
You could use a
That's what
map.
I was thinking about.
So then the map, if you use a map with the greater as the comparator function, then map.begin will basically be the first, the maximum frequency. And that is order one. You can get it in order one time. That's okay. So what all have I done so far? I have told that I need a frequency map. So I need a hash table to store the frequencies of every element. That's the first thing. The second thing I have observed that I will also need a hash table, which is where the key is the frequency and the value is something. Now I will have to see what the value is. Here the key is simply the element and the value is the frequency. This observation I did from my requirement that I need to retrieve the maximum frequency. So I told myself that to retrieve the maximum frequency, what I can do is I can keep a hash table wherein the key is the frequency. Now, for the value, I would need to store all the elements with that value, right? With that frequency. Why? Because I need, I basically I need all the elements, right? For that frequency. So now the next question is, how do I store these values? So these elements for a given key. So that decision will come from the observation, the tiebreaker observation. What is the tiebreaker observation? That I need to order these elements in the order in which they came. So, actually I need to order these elements in a last in first out order, right? Because for the same frequency, I need to first retrieve the element which came in the most recent, right? That is the observation. So this ordering, I know that I need a last in first out ordering, right? Last in first out, not first in first out. So this value I can use as a stack. and I can use a max frequency variable to keep track of the maximum frequency. So let's look at this. This is just some intuition, some that I gave you. Now let's properly define the operations. But let's quickly look at an example first before we define operations. So let's say the numbers are coming in. Let's say this is this is how the numbers are coming in. Let's say you have another 2 here and then a 4. So I have two things. I have a frequency array, a frequency hash table. And the next thing I have is I have a reverse frequency. It's sort of a reverse frequency hash table, right? Why? Because my key is the frequency here, and the value for each of them is a queue, is a stack. So let's build it. First number that comes in is 2. So what I do is I go to key 2 and I increment the counter. So this is a frequency thing. Now I know that for 2 I have 1 as I have frequency 1. Simultaneously in this reverse frequency, what I will do is this frequency that I have for this particular number, this frequency I will go to that corresponding key, and in that this will be a stack. In that I will push to. And I have a max frequency variable to keep track of the maximum frequency. So now max frequency will be updated to 1. This is the first operation that I did. Let's move on. We get at 3. I first come to frequency. I index by 3. I increment the counter by 1. So now I have 1. Now I go to 1 again from here. So now, and I will push 3. So now I have 2 elements with frequency 1, 2 and 3. And this is the order in which they came. The frequency, the max frequency is still updated to be 1 because it is 1. I get a 4 now. I will keep come to 4. This is 1. I will go here and I will push 4. Frequency still remains 1. 5, I will do similar things. Then go here and I will push 5. Now 2. Now here comes the part. So now I get a 2. So now I will come to 2 again. I will increment the frequency. So now the frequency becomes 2 for 2. So now from here I will go to 2. So let's say this is the slot for 2, for frequency 2. And in this queue, I will push 2 now. I will update the maximum frequency to 2 now. Now again 2 comes. I will come to this frequency. I will increment this to 3. I will go to the third slot. This will also be a stack. In this, I will push 2. Maximum frequency is 3. I will get a 9. I can, so I will get, let's change this to 3. 3. That's it. Let's not bother about this. So now I have a 3. I will come to 3. Increment this 2. From 2, I will go here. Push 3. Maximum frequency still remains 3 because this frequency is 2. I am just updating maximum frequency also by taking the maximum of whatever I have with the new frequency. Now I get a 3. I will come to 3. Increment this to 3. Go to 3. Push 3. And this remains 3. I mean, this is 3. So by the time I have inserted these elements, this is the picture. For 2, it is 3, which basically means that I have encountered 2 3 times. For 3, I have 3, which means I have encountered 3 3 times. I have encountered 4 one time and 5 one time. That is the meaning of this frequency array. This reverse frequency array basically tells me that frequency 3, I have elements 2 and 3, and 3 arrived later than 2. For frequency 2, I have elements 3 and 2, and 3 arrived later than 2. So the elements are repeated. Even though 3 has a frequency of 3, that means that it is present in all the 3 slots for frequency 3, for frequency 2, and for frequency 1. And my max frequency is 3. So this is how I insert. Is this clear? At least the insertion. This is order 1. Everything is order 1. Correct? Now let's do the tricky part of removing. It's not tricky, but there is one observation that is a little subtle. So now let's say I have to pop. So now I'm calling pop. So I will remove the max frequency, most frequent, right? So what will I do? I will look up the frequency from this variable. So this is 3. So basically that means that I have to remove the element of frequency 3. So from here, I will go to this. From 3, I will retrieve the most recent one, which is 3. So from this 3, and I will pop it. So I can remove this. And from this 3, I will go here and I will reduce the frequency to 2. Correct? Now this stack is non-empty. So the maximum frequency still remains 3, because I know what still remains whatever it was before, because I know that this stack has not cleared. So we are good so far. Let's pop another element. So when I'm popping another element, I will look up the frequency. It is still 3. So from this 3, I will go here. And from here, I will go here. I will see that 2 is the element. There is only one element in the stack now, 2. I will pop this. From this 2, I will go here. I will reduce the frequency of 2 to 2. And so this is done. Now I have to update the maximum frequency. Why? Because this has become empty. So now how will my question to you is, how will I update it, or what is the value that I will update it to?
Sir, about which value you are talking about?
The value of this variable max frequency. Why, Savio? Why will it be minus minus?
Because if something was appearing 3 times already, then it should have also appeared 2 times.
Yes.
So once I remove that, it will come back to 2.
Yeah. So you have to just decrement it by 1. And that reason for that is that, so yeah, that's the problem, Karan. You have to find the next highest frequency in order 1 time. That's the crux. One way you could do it is you could iterate here in the reverse frequency and you will get it. But that will take time, right? That will take order n time. We want to update it in order 1 time, which is where Savio said that it will be you just have to do a max frequency minus minus. And that will be the answer. Why? Because if something was inserted max frequency number of times, then it had a frequency of max frequency minus 1 also. Right? So 3 here had, when 3 was inserted, it was inserted in 3 stages, right? Frequency 1, then frequency 2, then frequency 3. So now once you have removed 1 3 of frequency 3, there still remains 2 more 3s, right? So the maximum frequency will just be 1 less. So you can do a max frequency minus minus to update it. Is this point clear to everyone? Why we do a max frequency minus minus? So then we are good. Then you keep popping. This is all order 1. Pop again. So now you get to 2. Now maximum frequency is 2. So go to 2, retrieve the element which is 3, pop it, go to 3, change the frequency to 1. But this stack is still not empty. So maximum frequency still remains 2. So keep doing this. This is all order 1. Let's quickly look at the code if this is clear to you. So we have 3 data structures here. We have a unordered map for the frequency. So that is the key is the key and the value is the frequency, which is also an integer. So both are integers. So let's call it frequency. You have another unordered map, which is basically the reverse frequency. So the key is the frequency and the value is the stack of elements. And let's call this reverse frequency. And you have one max frequency variable. So how do you push? So you do frequency x plus plus. So this is how you have incremented. Then you do rev frequency x. So whatever is the frequency, there you push x. And you update max frequency as max of max frequency and frequency x. So for that, just initialize max frequency in the constructor to 0. So that this is okay. Now let's pop. So popping is also fairly simple. Take the maximum frequency. So you know this is the maximum frequency. Go to the reverse frequency. Get the top element. How? So go to the reverse frequency. Index by max frequency. You will and get the top. Right? This will give you the top element. Pop the element. So popping is fine. Just pop it. So now you have removed from ref frequency. So just three steps. Everything is 3 steps. Remove from ref frequency. Now you will have to remove from frequency. So for that, do a frequency of top minus minus, and finally you have to update max frequency. So when you are removing from frequency, so when do you update frequency? When this becomes empty. So when ref frequency of max frequency, now you've already popped it, so but you can still do that. So this dot size is 0. So this stack is 0. This is the stack. If this stack is empty, then what you have to do 2 things here. Remove this key and update the max frequency. And that should be enough. And return the top. There is one more which is here, that if frequency of this top becomes 0, then you will have to remove that key from this map also, right? Now you can stare at this solution.
Sir, why you named the second hash table as rev frequency?
It's just reverse frequency, like the index is the frequency, right?
Okay.
So it's just, so index is the frequency. That's why. So generally, whatever you name a data structure is the value that is contained, right? The element. So when I say a frequency container or a frequency array, I mean that the elements in that array are frequencies, right? So that's why this is frequency. So because the elements in the map are frequencies, the values. So when I want to reverse that, I use reverse frequency. So basically now elements are not the values. The elements are the keys. I don't know how much that made sense.
So, like, I had a fundamental doubt, like, as a conceptual, how we'll get to know that where we have to use the unordered map and where we'll know that we have to use the ordered map.
Ordered
Like,
versus unordered, we will do a discussion. We have not talked about ordered maps yet, right? So we will do a thorough discussion on when you will get to know, understand.
Good.
Yeah, that you can keep your doubt, and if it will be
Sir,
addressed.
the
Yeah.
previous question I asked was like, if we are storing by index wise, like generally you are using rev frequency as that table, right?
So this reverse frequency is because, see, why is it called reverse is because, see, in this frequency array, you were storing, for every element, you were storing the frequency. Reverse frequency is because now you have reversed it. Now for every frequency, you are storing the elements.
Okay, okay.
So it's reversal in that sense. It's okay. I mean, you can name it something else. But do you guys understand these two steps, right? This step and this step? Karan, do you understand these two steps?
Sir, why do we need to erase?
Because if that, we need to erase the key, right? Otherwise what happens is, if you do frequency dot find, then that key will still exist. So in this case, it will still exist with a value of 0. So the problem with that is, when you, so that is a false positive, right? Because what happens is, when you, I mean, here it might not really affect, but the point is, if you are searching for any other key, let's say in future, then that key which should be erased is also in contention for a search, right? Or for any kind of operation, because it is a part of the map with some other value. So here it is a part of, in frequency array, it is still a part with value 0. In reverse frequency, it is still a part with an empty stack. But we don't want it to be a part of the map now, because the stack is empty. We want it to go away. Did that make sense?
Yes, sir.
Other questions? Everyone understands everything else? Shall we move on? Okay, so these are some data structure design. We have more. When we talk more data structures, we will have more design questions. Yeah, these are all with unordered maps. That's all with unordered maps. Everything, whatever else we have, are with ordered maps. So this is basically DS design. So try the question that I have given. So now we come to the third part of the class. If you remember the agenda that I shared, which is basically now we will talk about BSTs, or basically ordered search structures. So do you want to do it today, or do you want to call it a day? We have time, so we will be able to finish within time even if we start tomorrow. Like if you are already, if you too much has gone in your head today, then we can call it a day for today, and then we can resume from tomorrow. Or if you guys can take more stuff in, then I'm fine with starting now. So what is your take? Others? Guys, vote, because it's a democracy, and I will have to go with sorting. We will come, Ankit, don't worry. Let's others. So either all, yeah, it's fine. Yeah, I think Karan has a good idea. Let's just introduce for 5 to 10 minutes, and then we can like continue from tomorrow. So that's basically a good idea. So so far, if you remember hash tables, what did we say? We motivated the need for a hash table by saying that we have data that is coming in. Computers have a lot of data that keeps coming in, and what we need to do is we need to be able to insert this data efficiently, delete a data item efficiently, as well as search from within this data efficiently, right? That's the requirement that we motivated, and we used an example of Amazon, and we said that Amazon has tons of data that keeps coming in, right, from retailers and from suppliers from across the country. So it needs to insert. Then tomorrow, if you go and log into Amazon and search for an item, it needs to retrieve an item. So it cannot afford to have even a linear complexity for any of these operations, because it typically, that data is massive. It's, and you know that for 10 to the power 7 operations roughly, or 8 operations, you need a 1 second. So you cannot even afford to. So these datas are typically in gigabytes or in petabytes. So the number of operations needed, if you are doing a linear search on these data, will definitely take about more than a second, and we cannot afford that kind of a latency for these kind of tasks. And that's where we said that we need search structures which enables us to search elements in an efficient manner, and these search structures should be dynamic. So we should be able to insert and delete as well. And that's where we took a look at hash tables, and we said that hash tables are one search structures which gives us this facility or this feature to insert, delete, and search in order one time on average. So this is all that we have talked about. Now, this is fine. What if I tell you that in this hash table, find me the minimum element or the maximum element? I don't know the exact value of the maximum element. I need to find that. So how much time will it take? How much time will it take? Order n, right? Everyone understands. You have to go through the entire hash table. and find the maximum. Correct? So now people say that, okay, we are greedy, right? People are greedy. Like mankind has always been greedy. So now people say that, okay, this is fine. It serves my purpose, but I also want to retrieve most important elements for myself. So I need that data structure that I am about to design have this feature as well. So wherein because I have a container, just imagine I have container with items. Apart from inserting, deleting a random item and searching a random item, I will also at times need to retrieve the most important item. Like and typical examples of that, if you are taking an Amazon portal, is that when you look for, let's say, Colgate or toothpaste, then Amazon shows you a list of results, right, of all the kinds of toothpaste that it has, but it orders them, right? And how does it order them? It basically puts maybe the item with the most rating, like the best rating first and the least rating last. Let's say that is just one ordering. You can also customize the ordering. Let's say Amazon by default gives that ordering. So basically what has Amazon done? It needs to retrieve an item of a given importance, right? And that importance here is defined by user reviews or user rating. Whatever that importance criteria is, we can abstract that. That's not really important here. But the idea is that at times we want this feature as well from the search structures, that we want to retrieve, we want the ability to retrieve elements, significant elements from the container. And that's where hash tables have a drawback, that they don't allow us to search for the most important element or the least important element or element with the most priority in efficient time. And that's the reason we look for alternatives, because we are always greedy. And that's where we come to ordered search structures. So we say that definitely, if you remember the implementation of hash tables, in hash tables, we did not have any ordering of the keys, right? We just used a hash function to define a slot for that key, right? And we just said that it will go in there, the value. This is what we did, right? We took a key, irrespective of what the value was, we just passed it through the hash function. And that hash function need not maintain an ordering. So it need not maintain this ordering that if key 1 is greater than key 2, then f of key 1 has an ordering with respect to f of key 2, either greater than or less than, whatever. It does not generally ensure that. It is just a random hash function, a well-behaved hash function, whatever criteria we discussed yesterday. And it simply maps a key to a slot in the hash table and it puts it. So there is no ordering as such of the keys. And that's why you cannot retrieve items of a particular importance or whether of a particular from this hash table in efficient time, because there is no ordering. So you will have to go through all the elements, right? Had the keys been ordered in some way, then probably using the property of that ordering, you could have found the maximum key or the minimum key in efficient time, right? That's the idea. So there is no ordering, and that's why these are called unordered search structures. So that drawback led mankind to innovate ordered search structures. So in ordered search structures, typically you have an ordering of the keys. And because of that, what happens is you can get the minimum or the maximum in order log n, similar to binary search. You can delete any random element in log n in these kinds of ordered search structures. You can insert in log n, and you can search also in log n. So this is all log n. This is average case, best case, worst case, everything. Worst case, this is log n. Best case can be order 1. Everything is log n in these ordered search structures. Worst case, getting the minimum, maximum, insert, delete, search. So at the cost of the ordering, what is the cost that we paid for the ordering? The price that we paid is this, that these operations are no longer amortized order 1 or average on average order 1. They are now log n. That's the price we paid. But what was the benefit we got? We got that this benefit, that this now is no longer n. This is log n. So what I have told you so far, just to summarize, I told you unordered search structures and I told you their drawback. And I just introduced ordered search structures and I just told you their USP. USP is a unique selling point, as we were talking about the other day. So the USP is that it lets you do all these 4 operations in log n time. So that's basically an introduction to ordered search structures. Tomorrow, quickly in the first 30 minutes or so, we will look at how these order structures can be implemented, and which basically makes us achieve this log n complexity for these. Then we will look at applications of ordered search structures, and we will do DS design on ordered search structures. And then finally, we will go for heaps. Heaps is also on ordered. So we have 2 ordered search structures that we will basically be talking about: heaps and binary search trees. Heaps are not technically odd search structures, so you can like choose not to put it in this category also. It's okay. Okay. तो ये पूरी राम कहानी समझ आई सबको, जितना भी प्रवचन दिया अभी मैंने? Yeah. All right. So tomorrow we will continue from here, and I will paste some more questions. Try this peaking iterator also. This is a good data structure design question. This is a simple question, but it's a good question. I will tell you the number also. This is 284. I will paste these questions on Slack also, but for people who can't wait, you can take them down now. So 284, try this question also. And हो गया. Yeah, try this. And we will also have to cover hashing with 2 pointers. So try these questions also. We will come back to these questions tomorrow. These are hard questions, so we will start doing them tomorrow. Okay. So try these questions as well. We will see tomorrow. We will continue. Okay, so I will just stay around for a couple of minutes. Class officially is over. Thank you for joining. Good night. Take care and stay safe. I will see you guys tomorrow. If you have any questions, I'll just stay back for a couple of minutes and I can answer those questions. Otherwise, I will end the meeting.
Sir,
yeah.
The question that we are doing, like anagrams wala. So I saw a thing called tri-data structure.
Yeah.
Where we will use that.
So we will talk about it when we do. Okay. स्ट्रिंग के लेक्चर में ट्राई डिस्कस हो जाएगा. थैंक यू.
स्ट्रिंग ओके.
हाँ, तो वो हो जाएगा उस टाइम पे हम लोग कवर कर लेंगे. Amortized is average. Like it's different from average. It's amortized. This is average. Like it's little different from average, but you can take it to be average. Like unless you want to really go into the technical detail. Like then you will have to go into probability statistics. So how random function returns in order one? So I will share some article wherein you can see how computers simulate random numbers. So typically there is a way they do it. Okay, so I will share a reading material with it. You can go through that. How so and there is computers, like just for GK, computers generally the numbers that they generate are not truly random. They are pseudo random numbers. So because of the way they generate it, it's not truly random. Like so yeah, that's also one thing to keep in mind. So but generally we are okay with them generating numbers. Like they're not truly random. If we had to find one important item, we can do it in the maximum frequency. You are talking, Karan? In the maximum frequency stack, right? In the maximum frequency stack, what do you mean if you saying if we had to find one important item?
Sir, I'm talking about that minimum that we had to find, that minimum element. That question we did today.
Minimum element. You're talking about max frequency stack, right? एक ही stack वाला question तो एक ही किया. अच्छा, you are talking about main stack, right? The first question, are you talking about that?
Yes, sir.
The first question of the entire class.
Yes,
wherein
sir.
we have to find the so what is the question usme? If we had to find one important item, what does that mean, one important item?
अगर जैसे मैक्सिमम अगर हमें निकालना हो तो उसमें फिर मैक्सिमम निकाल लेंगे वैसे ही करके, तो एक तो मिल ही सकता है हमें मैक्सिमम.
मैक्सिमम मिल जाएगा, मिनिमम नहीं मिलेगा. मिनिमम रनिंग मिनिमम नहीं निकाल सकते आप, प्रॉब्लम वही है. आप सोच के देखो, जैसे आप अपडेट करते हो ना मैक्सिमम को, वैसे मिनिमम को अपडेट नहीं कर सकते, क्योंकि फ्रीक्वेंसी फर्स्ट टाइम 1 होगी किसी एलिमेंट की, तो आप मिनिमम फ्रीक्वेंसी को 1 कर दोगे और वो हमेशा 1 ही रह जाएगा, है ना. व्हाट आई एम सेइंग इज you cannot do running frequencies for minimum. That's actually a good question. अभी हम लोगों ने क्या किया, हमने मैक्सिमम फ्रीक्वेंसी कैलकुलेट करने के लिए व्हाट वी वर डूइंग वाज कि जब भी फ्रीक्वेंसी बढ़ रही थी किसी एलिमेंट की, तो वी वर अपडेटिंग द मैक्सिमम फ्रीक्वेंसी वेरिएबल, राइट, विद द न्यू फ्रीक्वेंसी, लाइक द मैक्सिमम ऑफ व्हाटएवर इट हैज एनकाउंटर्ड एंड दिस न्यू वैल्यू. तो उससे you can keep a running maximum frequency, but you cannot keep a running minimum frequency in a similar fashion, is what I'm trying to say. Why? Because it is the minimum. So the problem here is, if you do this, minimum frequency is minimum of minimum frequency, and now the new element, the frequency of the new element that you encountered, m of x, then this will always give you 1. Because the first time you inserted an element, the frequency became 1, the minimum frequency value took 1. After that, you keep incrementing. You make it 2, you make it 3, then you take another element with frequency 1. So now for this picture, the answer should be 1, right? But your answer for this picture, your answer should be 1. Now let's say you insert another, so now you have this. So now for this picture your answer should be 2, right? But your answer will always remain 1. because the first time you inserted it became 1 and it cannot go any minimum than that. So always, because you are doing a plus plus here.
Okay.
ठीक है, तो you cannot keep a running minimum frequency. तो minimum frequency के लिए you will have to keep a reverse frequency. Like we will see questions wherein we have to find a minimum frequency. Here we were able to update the max frequency by when removing also, because of the property in the frequency question that if an element has frequency k and you've removed it, then it now has frequency k minus 1. In hash table 0 plus plus is supported, but okay, but what? But int a plus plus is not supported. So that's because when you do a table 0, when you reference, so see, there are two things. When you reference a hash table by a key for the first time, what it does is, if that element is present in the table, then it returns the value. Otherwise, it creates an entry with and initializes the value to 0. So when you do a table 0 for the first time, even if key 0 is not present, if key 0 is present, it will return you the value for table for that particular key. But if 0 is not present, then what it does is that it creates an entry for 0. And the value that it gives to that key 0 is also 0. It just does that. So if you want to avoid that, whenever you reference it, so this could lead to a lot of problems when you are actually coding. You might unknowingly be creating elements when you are just finding elements, right? When you look for a key. So that's why when you look for the key, you should never do table in square bracket key, because if that key is not present, it will create it, so that the next time you will get a false positive that that key is present, whereas that key is actually not present. So that's why whenever you are looking for a key, you should always do table.find. Table.find is safe. It does not create, it just returns whether it is present or not.
So like in case of the ordered maps, when we initialize it, like does it by default gives us a element value of -1 or something like that? Because I've seen some questions where it was during the initialization, it was it had to do nothing, but it was returning simply values of 0 by default when I was only
0
printing.
initialize हो जाता है वो by default. मतलब
अनऑर्डर्ड और ऑर्डर दोनों के केस में
सारे मैप्स के लिए वो 0 इनिशियलाइज हो जाता है जब वो क्रिएट होता है, अगर आप वैल्यू नहीं दे रहे हो क्रिएट करते वक्त. सो सी देयर आर टू थिंग्स. व्हेन यू रेफरेंस अ की, अ मैप विथ अ की फॉर द फर्स्ट टाइम, तो वो क्या करता है ना कि वो उस मैप में वो की के लिए 0 इनिशियलाइज कर देता है, क्रिएट भी कर देता है अगर वो प्रेजेंट नहीं है तो. व्हेन यू डू समथिंग लाइक दिस, so इसलिए you should avoid doing this if the key is not present. That's why you should always have this under a bracket, under a cover, जहां पर आप श्योर हो कि ये की में एग्जिस्ट करता है.
सर अगर मैंने खाली मतलब जैसे इनिशियलाइज किया अनऑर्डर्ड मैप इंटेंट एमपी, तो तभी भी जो मतलब
नहीं की वही तो, तब एम्प्टी है वो मैप, उस टाइम आपके पास कोई भी की नहीं है उस मैप में. बट प्रॉब्लम ये है कि जब आप ये करते हो ना, ये तब बन जाता है. फॉर कोई की अगर नहीं है मैप में और आप उसके लिए ये कर दोगे तो वो की क्रिएट हो जाएगा उस मैप में, तो प्रॉब्लम वहां पर आ जाता है. तो इसलिए यू शुड नॉट रेफरेंस a key which is not present in the map through this. You should never do that.
ओके सर।
मतलब समझ आया आपको? शुरू में वो एम्प्टी है, शुरू में ऐसा नहीं है कि वो बहुत सारे कीज बना दिए उसने विद वैल्यू 0, वो ये नहीं किया कभी, ये पूरा खाली है। उस टाइम आप m डॉट साइज करोगे तो 0 ही आएगा, और m डॉट फाइंड करोगे किसी पर्टिकुलर की के लिए तो वो m डॉट एंड ही आएगा उस टाइम पे। बट अगर आपने गलती से m ऑफ 3 को कुछ कर दिया, मतलब लेट से आपने सिर्फ चेक ही किया कि इफ m ऑफ 3, आपको लगा कि अगर 0 है तो मतलब एग्जिस्ट नहीं करता है, तो आपने ऐसा कुछ कर दिया कि सी आउट डजंट एग्जिस्ट, ऐसा कुछ कर दिया। सो नाउ व्हाट हैपेंस इज, नाउ इफ यू डू m डॉट फाइंड 3 ना, तो वो इट विल रिटर्न ट्रू, मतलब it will return not true, मतलब whatever it has to return the iterator, but basically this will return true in the sense that this key will be found in the map, because आपने ये गलती कर दी। जब भी आप रेफर कर लोगे किसी की को तो वो अज्यूम कर लेता है कि की प्रेजेंट है, तो की नहीं होता है तो वो बना देता है। जस्ट C++ का सिमेंटिक्स है, मतलब सिंटैक्स है।
ठीक है सर।
Any more questions? All right, guys. Okay. Good night then. Take care. I will see you guys tomorrow, and I will end the meeting then.